So we are in the middle and nearing the end of showing, proving the LP boundedness of our Calvin-Sigmund operators on, right, so right, our ultimate goal, of course, is to show that K is a Calvin-Sigmund distribution. And this operator, given by convolution against K, for F in Schwartz class is bounded on LP. Right? And then you can extend from there to all of LP. Okay. And you remember where we are? We are in the middle of getting the weak type estimate, right? We showed the first day, very first day, we showed the L2 boundedness, which is easy because if you have a Calvin-Sigmund distribution, then its Fourier transform is a bounded function. And now, having obtained the L2 boundedness, we're going to go for, we cannot get a 1 boundedness, but we can get this weak 1 bound. And then we'll interpolate, and then we'll use duality, following the lines of stuff that has happened before. Okay. So, right, so we're right now in the middle of the weak 1 estimate. That is that there exists a bound such that for all F in L1 intersect L2, and all alpha greater than 0, we have control on the size of the set where the operator, where T of S is greater than alpha, that's controlled by A over alpha times the L1 norm of F. And I think in the notes I forgot to put the L1 norm of F here, which makes it ridiculous. Okay, so if I see in my current notes I've again forgotten to put it, so that means probably in the previous notes I forgot to put it as well. Okay. And remember the idea of the proof, the strategy is to use, as usual, the Calvin-Sigmund decomposition. Right, you decompose F at height alpha into good plus bad, right? And what we showed last, and then you say, well, look, this set where this thing is, because T of F equals T of G plus T of B by linearity, right, this is the convolution operator, we know that the set where this is bigger than alpha is contained in the set where this is bigger than alpha over 2, union the set where this, because if they're both less than alpha over 2, then the system is. Okay, and so last time we showed that we had the right bounds on this. Oops, so this doesn't make any sense. The measure of this set is less than or equal to the sum of the measures of these sets, because this set is contained in the union of those sets. Okay, one should not try to change one's lecture on the fly. That's the moral. Okay. Even the smallest changes can derail it. Okay, so last time we showed that that indeed the measure of this set is controlled by the L1 norm divided by alpha. Okay. And that was pretty straightforward. We use the L2 boundedness of T. We use Chebyshev's inequality and the L2 boundedness of T. And then subsequently we needed to use the weak 1-1 boundedness of the maximal, Hardy-Lewin maximal operator. Okay, so what we're left with is what we're left with is showing that this guy satisfies the analogous, the similar bound. Okay. So, okay. And here, we're going to use the fact that this bad part is actually pretty good, in the sense that it is, so call the bad part is the sum of these guys, each of which is supported. So you've got your E alpha, right? You've got your Whitney decomposition. You have your Whitney decomposition. Each of these guys is supported on a cube of the Whitney decomposition, right? And each satisfies the cancellation condition. Right? So where the support Bk is contained in some Qk, and the integral of Bk is 0, right? And also we have control on the average, right? That the average of the average of the absolute value is controlled by C alpha. Right? So it's not as good. It's not good in the sense of G being good. G was bounded by C alpha everywhere, right? Was pointwise bounded by C alpha. But we do have these three properties, and these turn out to be good enough, even though we call it bad. Okay. So what you notice here, of course, is that this says that Bk is if we divided Bk by C alpha times the measure of the cube, right, then this would be less than 1. Right? And so in that case, the thing that we'd be dealing with would be a 1 atom. Right? So in other words, Bk is C alpha is some constant times a sub k, where a sub k is a 1 atom, is a 1 atom. Right? Supported on Qk. So Bk is almost a sum of 1 atoms. And that would be good, because we know something good about how the operator behaves on 1 atoms, right? We have this thing because of the Hormander condition, and the Hormander condition gives us that the integral of the absolute value of T applied to the atom on the complement of the double of the ball is controlled by some constant. Using that selection. Okay, so we want to remember what our goal is, right? We want to control this thing. Okay. And so the way we're going to do it is we're going to break this into 2 parts. As before, so here's the strategy. We will take the set of concern. And we'll break it into 2 parts. This will be equal to the places where TB x is bigger than alpha. I'm sorry, this is alpha over 2, because we have alpha over 2. This will be E in some set, union E not in that set. So we're just going to split the set into 2 parts. And this thing will be called E alpha star. And this E alpha star will be some modification of the E alpha, involving double balls. The double balls in order to use our control on TA. Okay. Right. Okay. So here we go. What do we mean by E sub alpha? What do we mean by E sub alpha star? Okay. Right. Here's your E alpha. What we do is we take each qk and we surround it with a ball. Okay. Let bk be the ball surrounding qk. So let bk be the smallest ball containing qk. As usual, then bk star be the concentric level. And then we're going to let E sub alpha star be the union of the BK stars. So we take concentric doubles of every ball containing QK. We take the union of those guys. And that will give us a fattened, right? That will give us into a fattened D alpha. That will give us D alpha star. Okay. Notice that if we look at the measure of the alpha star, right, that's controlled by the sum of the measures of the BK stars, of course, because those guys cover it, right? But the measure of the BK stars is just some constant times the measure of the BKs. Right? Because they're just expansion. Right? It's just an expansion of the BKs. Right? But the sum of the measures of the BKs gives you the measure of E sub alpha. Right? So we get this is actually a constant times the measure of the alpha. Right? So this thing is the measure of the fattened guy is comparable to the measure of the original guy. And that's good, right? Because then you don't really have to worry about this part. Right? Very crudely, so the measure of that first set, where TV, we're just going to be very crude about it and say, well, that's smaller than the measure of E alpha. Right? Some constant times the measure of E alpha. Right? And we have control on the measure of E alpha by the weak one-ness of the Hardy-Little maximum operator. Right? So this is controlled by some constant over alpha times the one effect. So that first part we sort of almost give up on. We say we don't care about. We're not even going to think about this. Because we have the necessary control on the size of the set. So that part is easy as long as we understand the maximal the maximal operator. So the more subtle part is the second. Right? How do we deal with this thing? Any questions? Any questions? Any questions? Okay, pretty straightforward, right? The subtle part is the second. Like, how do we control we want to control the measure of this set. Let me make the following observation that if S is a bounded set, then the measure of the set, the measure of the x in S, where TV x is bigger than alpha over 2, is, by Chebyshev's inequality, controlled by 2 over alpha times the integral of TV over S, and the also by TV over S, right? Just by Chebyshev. Oops. Sorry, there are like, I don't know how many ways to spell Chebyshev. So the one they use in the text is this one. So, yeah, okay. So by Chebyshev's inequality, and then this is controlled by the triangle inequality by 2 over alpha. What's this? Okay. So if you let S be E alpha star complement intersect some ball with radius r, and let r go into infinity. Let's say some ball with radius r centered at the origin, and let r go to infinity. You get this. You get this. You get this inequality that this is controlled by 2 over alpha times the integral, so it should be over S, over E alpha star complement, E alpha star complement, dB. Okay, so to control this set, it suffices to control these guys, right? But these guys, right? The complement of E alpha star is contained in the complement of BK star. Right? BK star is inside E alpha star, right? So the complement of that is going to contain the complement of E alpha star. So this is bounded. So this in turn is bounded by 2 over alpha equal this thing BK star complement TBK. Right, and so it's sort of clear what's going to happen now, right? We are taking this guy against some multiple of 1 atom, right? So remember, BK equals C alpha and QK times some 1 atom, right? So this equals 2C, 2 times the constant. C and QK, right? And QK times the integral over the complement of the double double ball of the of T applied to the 1 atom. Sorry, that's undusted. I'm crying. say that at some point I won't break down in tears. But not today. Okay. Right. And that's good, right? Because each of these things is controlled by some constant. These guys are all controlled by some constant, right? And so we get ultimately some constant times the sums of the measures of the QK, and that's a measure of the alpha, right? And we know that that is controlled by some constant of alpha as the L1 by the Hutting over last because week one on boundedness. William, your brow is knit. What's wrong? Remember,
bounded by A?
This is bounded. This is what we did last class. We showed that because the associated function to the Pauli-Zygmunt distribution satisfies the Hormann condition.
Oh, yeah. Okay.
Yeah, remember that there's this Hormann condition.
Yeah,
on the right, not one. But there's this Hormann condition, that said that if you satisfy this Hormann condition, then this thing is controlled by A.
Sorry.
That's it. Okay. So that's the thing. That Pauli-Zygmunt operators have this nice behavior on atoms as long as we stay off of the support of the atom. As long as we stay away from the support of the atom.
Okay.
Okay. Any questions? So, okay. So the rest of the proof is sort of smooth sailing, relatively speaking. Right. We have the weak type inequality. We have the L2 inequality. We have the L2 boundedness. And we will we'll put the two of them together to get a strengthened weak type inequality. That strengthened weak type inequality will give us the LP bounds for P between 1 and 2. And this procedure, if you generalize it, is the so-called Marcinkiewicz interpolation theorem. That if you have weak 1, 1, and you have LP bounds, then you can get the bounds then you have all P between 1 and P. You have all P between 1 and that P that you had before. Right? If you have weak 1, 1 and LP not bounds, then you have all P between 1 and P not. It actually goes a little bit farther. There are actually several generalizations of it. You don't need to have strong LP bounds on this side. It could be weak so-called weak PP bounds, and you can also generalize to. I'm pretty sure that you can generalize to. It doesn't have to be weak 1, 1 bounds. It could be like weak PQ bounds here and weak P, which we don't know about yet. But anyway, there's like a whole range of interpolation things that spring out of this idea. Okay. So first let's get the strengthened weak type inequality. So if F is in L1 intersect L2, then the measure of the set where Tf x is bigger than alpha is controlled by some constant. Well, what we had was some constant over alpha times the L1 norm, right? But in fact, we can do better. We get something a little bit better using the things that we have. Okay, and I should say that I'm not putting up all the hypotheses here, right? This is of course a Kaplan-Sigma operator, right? So just assume that all the last few propositions have all been under the grand theorem, which is you have a Kaplan-Sigma operator. So 1 over alpha times the integral of the absolute value of f over the set where f is bigger than alpha, plus 1 over alpha squared over the set where f is less than alpha of the square of the absolute value of f. So we have this sort of refined version of the weak type inequality. And the proof of it is as follows. We're going to do a split. So fix alpha, and we split f into f1 plus f2, where f1 is equal to f on the set where the absolute value of f is big. So it equals f where the absolute value of f is big, and it's 0 where the absolute value of f is small. F2 is f, of course, by definition, f minus f1, so it's going to be f on the set where the absolute value of f is small. And it will be 0, oops, it's small, and it will be 0 where the absolute value of f is big. Okay, right, so we know what we're going to do. At this point, we have the set. We split the function into 2 parts. Right? We're going to divide the set into 2 parts. So then, as usual, the measure of the set where this thing is bigger than alpha is controlled by the measure of the set where this guy is bigger than alpha over 2, plus the measure of the set where this guy is bigger than alpha. Okay. Okay, so then it's kind of easy, right? What do we know about this? What do we know about this? We have the weak type estimate already. We use the weak type estimate here, right? This is going to be controlled by 2 over alpha times the L1 norm of F1, right? But the L1 norm of F1 is the integral of the absolute value of f over the set where f is bigger than alpha, right? Because of the definition of F1. And then the other side is sort of equally easy. By Chebyshev inequality, this is controlled by 2 over alpha squared times the L2 norm squared of TF2. By Chebyshev. the L2 boundedness gives us that that's bounded by some constant. So constant over alpha squared times the L2 norm times the L2 norm of f squared, which is the L2 norm of f restricted to this end. Right? Because f2 is f where the function is small. At 0 elsewhere. And that's the end. We get that this size of the set is controlled by some constant times 1 over alpha times the integral of this thing over the set where it's big, and times some constant over alpha squared times of the L2 norm on the set where this is small. So that's, like I said, it's pretty smooth sailing from here on in. And this inequality, this refined inequality will give us the LP balance. Okay. So here we go. So we have that now. We use the lemma to get that. Now we get the claim that T is bounded on LP, or P between 1 and 2. We have 2 already, so this we already know. Now, P equals 2 already. Okay. So the proof of this will follow basically what we did the last time when we were proving the LP boundedness of the Harding-Littlewood maximal operator. We let lambda of alpha be the measure of the set where TF is bigger than alpha. Right? This is the so-called distribution function. Not at all related to the distributions that we've been dealing with. Not the same thing. Yeah, this is just a measure of the set where the thing is bigger than alpha. You may recall that we can express the LP norm of the function in terms of its distribution function. So this is one way of getting some estimate on the LP norm. You say, well, I'm going to translate this to a statement about the distribution function, and now we have this lemma which tells us something about the distribution function. Right? So what we have is that that this is controlled by some constant times the integral 0 to infinity, alpha to the negative 1 over p, times the integral of f the value of f over the set where f exceeds 1 alpha to the 1 over p, plus the integral from 0 to infinity, that's the other guy, using the other part of the lemma. So integral less than equal to 1, alpha to 1 over p, plus 3 dx. So by the lemma. Okay. But then we just do Fubini's theorem. We say, okay, well, this thing here is going to be equal to the integral, you change the order of integration. This is going to be integral from 0 as alpha ranges from 0 to f to the p, right? Of alpha to the 1 minus p, the alpha dx. That turns out to be some constant times the LP norm. LP norm with f to the p. This thing over here, again we change the order of integration. This thing equals the integral of f squared. Alpha, in this case, goes from 0 to, from f to the p to infinity, and we're integrating into the -2 alpha to alpha, which equals p sub p times the LP norm of f to p. In this case, we need p to be bigger than 1, and in this case we use the fact that p is less than 2. When you do the integration, we need p to be less than 2 for the integral to converge. Okay, so we get that that pf is controlled by some constant, times that t is bounded on LP. Because we have the LP norm to the p power of tf, and on the right hand side we have the LP norm of f to the p. Take the p through both sides and you're done. Okay. Any questions, Anna? You look like you're thinking. Okay. So yeah, maybe for homework I should actually assign the general marks of Cambridge thing. But it's basically here, so maybe it would be no work at all. It's no fun. Okay. So we're getting there. We're almost there. Right? We almost finished. We have the boundedness of t between 1 and 2 and f2. Right? And now we just need to use duality to get it for p greater than 2 and less than infinity. So the last plane, final plane is t is bounded on LP for p greater than 2 and less than infinity. I feel like we should sort of like end the course right after this happens. Just declare victory and then run. But no, I'm afraid there's more. Okay. Okay. So we will need the following operator. Define T star by convolution with K star, where K star is the guy whose Fourier transform is m bar. Okay, so you just take the complex conjugate. So this thing is the complex conjugate. The Fourier transform of K star is the complex conjugate of the Fourier transform of K. Okay, then for F and G in the Schwartz class, the Quantrell's theorem gives that TF G bar equals M F hat G hat bar dc. Which equals, again by Quantrell's theorem, F of T star G bar. So just by Quantrell's theorem, right? That we can put hats on both of these guys, right? So by Quantrell's theorem, this is equal to TF hat G bar hat, which gives us this, right? And then by Quantrell's theorem, you can take the hats off, right? And so you get back to here. Okay. For F and G in L2, the above still holds. This still holds via approximation by Schwartz class functions. And the fact that T star is bounded on L2. T star itself is a Calvin Sigmund operator, and so the proof that we showed earlier, showing that T was bounded on L2, shows that T star is also bounded So I should be honest that I think this works. I think this is how it works, but I haven't checked. This fact I haven't checked. So in my notes I have this big sign check. Okay. Let me just assume that's right. Okay. So we're trying to get T to be bounded on P for P greater than 2. For P bigger than 2, we know that the LP norm of TF can be obtained as the supremum of the absolute value of TF against G bar, where G is simple, and the LP prime norm of G is less than or equal to 1. This was from the duality stuff that we did in chapter 1. Do you see what's going to happen, right? We can switch this over, right? We switch this over to F of T star G bar, right? And we know that we know that so F is in LP, we know by Halber's inequality, right, that this is controlled by the LP norm of F times the LP prime norm of T star G. But T star prime, T star is bounded on LP prime, right? Because P is greater than 2, P prime is less than 2, right? And we know that this guy, being a Calvin-Sigmund operator, is bounded between on P between 1 and 2, right? So this thing is controlled by the LP prime norm of T star times the LP prime norm of G, which is less than or equal to 1. Right. So we get that all this stuff is bounded by some constant times the LP norm of F. Right? And so T is bounded on LP as well. So this is not exactly how the original proof ran, but it's basically the same way as the way the original proof ran, but sort of reorganized in hindsight with knowledge about atoms and stuff. It's pretty cool to see how Stein rephrases everything with in knowledge of how the atomic decomposition became central. Yeah, and it's sort of even more cool to see how all the ideas of how the ideas of the atomic decomposition were in fact that was the insight that the behavior of singular integral operators on atoms can be controlled. And that turned out to be very crucial. The end. No, sorry. So like I said, I would like to just say that's the end of the course, but we still have a few more weeks left, and still a few more 100 pages, I think. So at least more than 200 pages left in the book, so there's plenty more to do. I think I must have been insane when I was thinking at the beginning. Before I started this course, I was thinking, okay, we're going to get through the whole text in this one semester. And that's what I was sort of planning at the start. But no way. This is a lot of material. A lot of material. Yeah, I sort of regret that we're not going to go farther. Those of you who are still here next year, if you want to do a reading course and go farther, it will be painful, but I'm up for it. Yeah, because there's a lot of important stuff in the second half of the book, right? And we're in striking range. We're in striking range. So, yeah, that would be extremely painful for me, but at the same time desirable. Okay, so let's go on to chapter 4. Okay. Maybe we will finish one half of the book by the end of the term. Okay, so chapter 4 is about the Baire Category Theorem. How many of you seen this before? Baire Category Theorem? Okay, some of you have. So the Baire Category Theorem and applications to functional analysis, the closed graph theorem, open mapping theorem, this sort of stuff. Yeah. So okay. So some of you have seen this before, but some of you maybe haven't. So let's give this stuff is, I think, far more low level than of a far lower level than the stuff we've been doing up to now. So it would be like a nice break for everybody, I think. Yeah. In fact, I have the impression that this entire chapter was almost assumed in my own when I took functional analysis in graduate school. Like the professor just said, okay, so there's this result, this result, this result, this result. And now let's go on. Right, so I think he just expected us to read it. Yeah, that was maybe first day of class. Okay, that's my that's my memory. Who knows if that's actually what happened? Okay, so so this will be very simple. X a metric space. X a metric space with metric B, and possessing with the topology induced by D. Right. So you've got these balls. The balls define open sets. Right. Set is open. If any point inside it can be contained in the ball, it's contained in the set. Okay. So we call some notions the interior of a set. The interior of the set is the set E is the union of all open sets contained in E. The closure of a set is the intersection of all closed sets contained in E. So easy that we can take a bathroom break. Okay. Right. You have some set in the metric space. If its closure equals the whole set, we say E is dense in X. Or if we take the closure of a set and then look at its interior and it's empty, then we say E is nowhere dense. So the interior of the closure is empty, then we say the thing is nowhere dense. And now we have the main definitions. So if E can be expressed as a countable union of nowhere dense sets, then we say E is of the first category. If E is not of first category, then we say E is of the second category. If E complement if E is complement of a set of the first category, and we say E is generic. So these guys are also called meager. Say the set is meager. So the meager sets are complements of generic sets. Generic sets are complements of meager sets. Because the terms first category and second category don't really give any, they're not very colorful. Right? What do they mean? There's no, so meager is maybe more descriptive. It's a countable union of nowhere dense sets. Some not very sparse. Maybe I should let you guys do the lectures for the last chapter of the book. Or maybe I should have Chen do the lectures for the last chapter. But CGU students, you guys don't get any chance to teach, basically. Right? There's no TA positions right now. Okay, so here's the main result. Baire Category Theorem. If X is a complete metric space, remind me to tell you something after class. It's not mathematical. I guess I can sort of. This is not related to mathematics at all. But where are you from, Candice? Where are you from? Like ethnically?
Where my friends are Vietnamese.
Vietnamese? Okay, forget it. So anyone, well, anyway. If X is a complete metric space, then I guess I shouldn't be so limited in my thinking. This is not relevant at all, but the former vice president of Taiwan is going to give a talk at 12 o'clock today in Ferry. If you're interested in Far East politics, then this should be pretty interesting. Okay, if X is a complete metric space, then X is not meager. And now I realize that a second advantage of the word meager is that it's shorter than writing, not of the first one. Okay, so we'll prove this by contradiction. Suppose X is meager. Then, X is expressible as some countable union of nowhere dense sets. Expressible as some countable union of nowhere dense sets, right? So, without loss of generality, we may assume that all Fn are closed. Right? If they're not closed, just close them all. Nowhere dense, remember, means that the interior of your closure is empty. Right? Well, if the interior of your closure is empty, then if you close it, certainly the interior of your closure is still empty, right? Because your closure doesn't change things. without loss of generality, we assume that all these guys are closed. Okay, so X is expressible as a union of these closed, nowhere dense sets. And now we consider the first of them. Consider F1, right? It's a nowhere dense closed set, right? And you say, well, look, you know, it doesn't take up the whole space, right? So there's some point in the complement. In fact, there's a ball in the complement. Right? There exists a ball B1 contained in F1 complement, say of radius R1. Such that B1 closure is still contained in the complement. So B1 closure doesn't intersect F1. So, now we consider F2, right? We know that B1 intersect F2 complement is not empty, right? Right. The point is that, sorry, let me say it like this. If B1 were contained in F2, then F2's interior would not be empty. So we know that B1 intersect F2 complement is not empty. Right? So so there exists a second ball, B2, say radius R2, such that B2 closure is contained in B1, and also B2 closure is contained in F2 complement. We can take a ball contained in the complement of F2, and we can take that ball to be inside of B1. Because you take some point, there will be some point inside of B1, you take a ball around that point, inside B1. We may choose R2, so that R2 is less than a half of R1. Okay, and then you continue this way. Continuing, one obtains a sequence of balls Bn of radii Rn, such that the Rn goes to 0 as n goes to infinity. The Bn plus 1 closure is contained in Bn, and Fn intersects Bn bar is empty. Now, choose a sequence of points, Xn, it's a Cauchy sequence, right? They form a Cauchy sequence, right? Because the radii of the balls are decreasing to 0. And so converge to some point x. Right? This point is really the point of the intersection of all the closure of the balls. Right? There's a single point in the intersection of all these balls. That point is going to be the limit. But this point being in every single ball means that it's in none of the Fn. Right? X is not in any of the Fn. Right? But that the union of the Fn was supposed to be all of the whole space. So we found a point that's in the space and not in the space. Let's see a contradiction. Okay, so that's the Baire Category Theorem. Any questions? Let me finish up with a corollary. Quick corollary. If X is a complete, this is a metric space, and E is contained in X. If E is generic, then it is dense. And the proof is pretty straightforward. Say that E is generic and not dense, right? Then E bar is not, is not all of X, and so there exists a ball such that B bar is contained in this open complement, right, of E, is contained in E bar complement, which is contained in E complement. Okay. Since E is generic, we know that E complement is meager. Right? That's to say, E complement equals the union of these is a countable union of nowhere dense sets. But then B bar equals the union of these intersections of these guys against B bar, right? Where these are nowhere dense. Well, in turn, these are in turn nowhere dense. But then that says that B bar is meager. But B bar with the metric is a complete metric space. Right? With the metric and the topology induced by it is this closed ball is itself a complete metric space. So it should be cannot be. It's not. That's a contradiction. So maybe you feel like you've gone back to your childhood and things are so simple now. Okay. Okay, so next time we'll continue along these, sort of, no wait, next time is an exam. But then after that, we'll continue sort of doing the easy stuff.